Okay, so the differential equation is y double prime plus 4y equals 8 with the initial condition of y0 equals 0 and y prime 0 equals 3. So what we're going to do now is we're going to write the Laplace transform of y double prime plus 4y equals the Laplace transform of 8. Okay, so here I took the Laplace transform of both sides. Well, we're going to. And y double prime plus 4, the Laplace transform of y equals 8 over s. So the place of 8 is 8 over s. And now we're going to write the Laplace transform of, oh, it's so funny. There we go. Okay, of y double prime equals s squared y, s minus sy of 0 minus y prime 0. Okay, so the Laplace of y double prime is s squared y s minus sy 0 minus y prime 0. Next, we're going to write s squared y as sy 0 equals minus y prime 0 plus 4y s equals 8 over s. Okay, so we transform the equation into this, and next we're going to write s squared y s minus 3 plus 4y s equals 8 over s. So now that I plugged in y0 equals 0 and y prime 0 equals 3, that gave us s squared y of s minus 3 plus 4y s equals 8 over s. Okay, for step 2, we're going to solve, well, okay, there we go. For step 2, we're going to solve ys. So let's start by writing s squared plus 4 y of s minus 3 equals 8 over s. So I combined the y's terms to get s squared plus 4 ys minus 3 equals 8 over s. So now let's write s squared plus 4 ys. Here I'm going to move the negative 3 to the right side. And so we're going to write equals, 8 s squared plus 4. Let's make this longer. There we go. Plus 3 s squared plus 4. Okay, now I'm going to divide by s squared. I'm going to divide by s squared plus 4. So y of s equals 8 over s squared plus basically this s squared plus 4 and 3 over s squared plus 4. Okay, so now we're going to do the partial fractions, apologies. So we're going to write 8 squared plus 4 equals a over s plus b s plus c. Oops, those are really... Okay, and then s squared plus 4. So I decomposed 8 over s squared plus 4 using the partial fractions. And now we're going to write 8 equals a s squared plus 4 plus b S plus C S. So multiplying both sides by S of S squared plus 4 gives us 8 equals A of S squared plus 4 plus plus BS plus C S. So now we're going to write, actually, okay, there we go. We're gonna match our coefficients. T equals 0. Okay, perfect, yay. Okay, so now I match the coefficients from S squared, A plus B equals 0, and from S, C equals 0, and from the constant term for A equals 8. So now we're going to write, let's see if I have room. Okay. We're going to write A over S squared plus 4 equals 2S minus 2S S squared plus 4. Okay, so that means that 8 over S of S squared plus 4 equals 2 over S minus 2S over S squared plus 4. So now we're gonna go into the inverse lap, and hopefully I have enough room. Okay, so we're gonna write Y S 2S minus 2S S squared plus 4 plus 3 S squared plus 4. So substituting back, y of s is equal to 2 over s minus 2s over s squared plus 4 plus 3 over s squared plus 4. So now, from the Laplace table, let's write this. 1 over s goes to 1. So let's write 1 over s goes to 1. And inverse Laplace form of, oh, there we go. S, it's an ugly S. Okay, there we go. S squared plus, oh my god, squared plus 4. Plus 4 cosine 2. And then, once again, 1 over s squared plus 4 equals 1 over 2 sine 2t. Okay. So the s over s squared plus 4 goes to cosine 2t, and the 1 over s squared plus 4 ended up going to 1 over 2 sine 2t. And so now finally we can write y t equals 2 minus 2 cosine 2t plus 3 over 2 sine 2t. So applying the inverse Laplace transform, I got this. And that finishes problem 1. Yay! Problem 2 is the power series solution problem. So first we're going to find the power series solution about x equals 0 for y double prime minus xy equals 0. So what we're going to do first, we are going to write, let's find a not awkward spot, okay. We're going to assume the series and differentiate. So we're going to write y of x is equal to the sum of n to infinity a sub n x to n. So I assume a power series solution of y of x equals this. Now we're going to write y prime of x is equal to n of 1 to infinity. So na sub n x n to x to n negative 1, sorry. Now we're going to write y double prime of x equals sum of n equals 2 to infinity n minus 1 a sub n x n minus 2. Okay, so now we're going to substitute into the dE. So we're going to write y double prime minus xy equals 0. So now I'm going to plug into this equation y prime minus xy equals 0. And I'm going to write, sorry, I'm speaking in like tense that like I already did. So sum of n equals 2 n minus 1 a sub n x to negative 2 minus x. Oh, it's an ugly x. There we go. And then sum of 0 to infinity a sub n x n equals 0. So substituting the series gives this expression. Next, we're going to write, well, we're going to multiply by x shifts the powers. So we're going to write total sum of 0 to infinity a sub n x to the power of n equals x, sorry, not x, total sum of n equals 0 to infinity a sub n x n plus 1. Okay, so that gives us that. And now we're going to write, okay, but first let me explain. So the equation becomes what I'm going to write right now, which will be the difference of two series. So total sum of n equals 2 to infinity n minus 1 a sub n equals n minus 2 minus total sum of n equals 0 to infinity a sub n x to n plus 1 equals 0. So the equation becomes this difference of two series. Okay, so now we're going to re-index both sums. So we're going to let k equal n minus 2. So let's write total sum of n equals 2 to infinity. Oh, it's an ugly infinity. There we go. n minus 1 a sub n x to the power of negative 2 n minus 2 equals k 0 of infinity, okay, and then k plus 2 k plus 1 a sub k plus 2 plus 2 x to the power of k. Okay, so for the first sum, I let k equals n minus 2, so it becomes this. Wait, let me retrace my steps to make, yes, it does, okay. Apologies. I got mixed up because there's a lot going on. This is my first attempt. Okay. So now we're going to let k. Oh, let k equal n plus 1. Okay. So now 0, infinity, and then a sub n x n plus 1 equals sum of k equals 1 to infinity minus 1 x to the power of k. Okay, so for a second sum, I let k equals n plus 1, so it becomes this. So now we're going to write, oh, let's see if probably won't have enough room. The total sum of k equals 0 to infinity. So k plus 2, k plus 1, a sub k plus 2, x to the power of k minus total sum of k equals 1 to infinity a sub k minus 1, and x to the power of k equals 0. Okay, so putting both reindex sums together, I get this equation. Okay, now we're going to separate k equals 0 term and get recurrence. So to do this, we're going to write k 0 turn to 1 x to the power of 0 equals 2a. Okay, perfect. So first, I looked at k equals 0 term from the first sum, which is 2a sub 2. Okay, now I'm going to write 2a sub 2 plus total sum of k equals 1 to infinity, and then k plus 2, k plus 1, a sub k plus 2 minus a sub k minus 1. And then x to the power of k equals 0. So the whole series becomes 2a sub 2 plus the sum from k equals 1 to infinity. And now we can write 2a sub 2 equals 0. A sub 2 equals 0. Okay, so since the coefficient of x to the power of 0 must be 0, 2a sub 2 equals 0, so a sub 2 equals 0. And then, let's see, let's try to fit this in here. So, for k is greater than or equal to 1, so k plus 2, k plus 1, a sub k plus 2 minus a sub k minus 1 equals 0. Okay, so for k is greater than or equal to 1, each coefficient of x to the power of k must vanish, giving us this equation. Okay, so the recurrence relation is a k sub plus 2 equals a k sub negative 1 over this, what we just wrote. So next we're going to generate the coefficients and final series. So to do this, we are going to let a sub 0 equals a equals b. Oops. Equals b. So I let a sub 0 equal a and a sub 1 equal b be arbitrary constants. So next we are going to write a sub 2 equals 0. So from before, a sub 0 equals 0. And we are going to write a sub 3 equals a over 6. A sub 4 equals b over 12. A sub 5 equals 0. A sub 6 is equal to a over 180. A sub 7 is equal to b over 504. There we go. So using the recurrence, I get a sub 3 equals a over 6, a sub 4 equals b over 12, a sub 5 equals 0, and a sub 6 equals a over 180. And a sub 7 equals b over 504, and so on. So we're going to write y of x equals a, so 1 plus x to the power of 3, 6 plus x to the power of 6, 180 plus 1, plus b, x plus x to the power of 4, 12 plus x to the power of 7, 504, plus, here we go. And so the power series solution completes this part. So now moving on to problem 3, which is solving the linear system describing the phase plot. So what I did this for is I wrote the system in matrix form x prime equals ax, where x equals x by the power of t, and a equals 2 by 2 matrix, which is this one. And then regarding eigenvalues, to solve the system, I found the eigenvalues by solving determinant a minus lambda I equals 0. Okay, so then I was in the process of writing a minus lambda I equals 2 by 2 matrix 3 minus lambda 1. Oh, let's make this bigger. There we go. 4 minus negative 2 and okay, there we go. So here's the matrix A minus lambda I. Okay, so moving on, we are going to write the determinant A minus lambda I equals 3 minus lambda negative 2 minus lambda. That looks like an x, but it's lambda. Minus 4. So the determinant is this. Okay, so now we're going to write 3 minus lambda negative 2 minus lambda negative 4 equals lambda squared minus lambda minus 10. So expanding and simplifying, I get okay, perfect. That's established. So we're going to write lambda again over 1 plus or minus square root 41 over 2. So solving that quadratic gives us this. So one eigenvalue is negative and one is positive. So now we can also write eigenvalue sub 1 equals 1 minus square root 41 over 2, and eigenvalue sub 2 equals 1 plus square root 41 over 2. So I labeled them. So now moving on to step 3, which is the eigenvectors. Sorry, step 3. Where am I getting step 3 from? Eigenvectors. So let's write for any eigenvalue. Sorry, for any eigenvalue lambda. X plus y equals 0. Y equals lambda minus 3x. Okay, so for an eigenvalue lambda, the first row gives us 3 minus lambda, and x plus y equals 0. So y equals lambda minus 3 and x. So I set x equals to 1 to get an eigenvector. So we're going to write matrix minus 3 lambda minus 3. So for lambda, so for lambda sub 1, I get v sub 1 equals 1 comma lambda sub 1 minus 3 to the power of t. And for lambda sub 2, I get v sub 2 equals 1 comma lambda sub minus 3 to the power of t. Okay, now for our general solution, we are going to write xt c b sub 1 equals lambda 1 t plus c2 v 2 e to lambda sub 2t. Okay, so the general solution of x prime equals ax is, but we're not done yet. So we're also going to write little 2 by 2 matrix. C1, 1 lambda, T plus C, 2, and 1 lambda, 2 minus 3, e 2 lambda, 2t. Well, I hope you can see that. Okay. Now to classify in phasor portrait, so lambda 1 is less than 0 and lambda 2 is greater than 0. So saddle point at origin. Okay, so because one eigenvalue is negative and the other is positive, the origin is at a saddle point. So stable direction along E1 as t approaches infinity. Unstable direction along V2 as t approaches infinity. So along the eigenvector v1 for the negative eigenvalue, solutions move toward the origin, and along the eigenvector v2 for the positive eigenvalue, solutions move away from the origin. Okay, so in the phase plane, there you go. In the phase plane, I drew the eigenvector lines to the origin and sketched the saddle shape curves coming near the stable direction and then get pushed out along the unstable direction. And that completes problem 3. Thank you so much.